For the sake of completeness, we can have a look at lateral inversion. So let's have a look at the rules first. After each reflection, the image is laterally inverted. So if we say a P in the mirror, say it was a flat mirror, you could have a P, and you have a mirror down here. It would be laterally inverted. This distance here would obviously be this distance here. Not particularly well drawn. If we reflected it again, we would put it back to its original way around. Despite the poorness of the drawing, hopefully the concept has been reasonably well understood. So after two reflections, the image is not laterally inverted. So let's have a look from an NCA question. Security mirror. On the wall, he notices that the mirror is curved, it bends outwards. So we know we're dealing with a convex lens. So draw the appropriate rays to show how his image is formed. So we're going to bring a ray in here, reflect it out, and then dot behind it. And then we're going to bring one in parallel to this principal axis, and we're going to use that to reflect it off in this direction. So let's see, have a look at those lines now. So this line here, we have to put arrows on it. We clearly have to show the direction that's involved. If we don't, and we have to use dotted lines behind, and we have to describe what we're seeing here. So it's real, diminished, and upright. If we don't put these lines on, we'll never get our merit. There are two major formulas that are available to Year 12 students. Let's have a look at these. The focal length is positive, so it's in front. It's negative for convex mirrors. This is absolutely essential in understanding how to do the calculations effectively. So we have an image, we have an object, and we need those. This has got a particular height. This is always positive. There is a distance from the mirror to the object. We call that DO. It's always positive. Can be in different values, but often seen in meters. The height of the image. So we use a convention. It's positive if it's real, negative if it's virtual. So this would be a negative value. If something appeared down here, this would also be a negative value. We need the distance from the mirror to the image. This is DI. And it's positive if it is a image that is real. If it appears in here, it's going to be virtual. So let's have a look at the formula in a bit more detail. 1 over the focal length is equal to DO plus DI. If we want to solve for F, is no more than doing 1 over DO plus 1 over DI, all to the minus 1. And we can rearrange accordingly, but we do have to watch these being negative values and these being negative values. You do need to keep your wits about you when you plug these in, and when you make a list of the information that you've got to be confident what you're dealing with. Remember, this is the focal length, distance the object is, often in meters, and distance the mirror is, again in meters. So this is how far it is to the image from the mirror. If you have a situation that is convex, the focal length is in here, so we create it as a negative. This is the mechanisms that examiners use to catch students out, because the mathematics is relatively straightforward. And the other thing that they do is that di is negative if it's virtual. The other part of this, that it's also a ratio for magnification. The ratio of the image over the object and the height of the image over the object. So if you think about it, if this number is bigger than that number, it's going to be a number greater than 1. If it's going to be, so then it's going to be a magnification. So you can either take it as a ratio of the distances or a ratio of the heights. So if you've got the magnification and you've calculated this, you can find out how big the object's going to be. So these are interchangeable, and you have to think very carefully of the information that you've got and the information that you're trying to calculate.